How can the postulates of quantum mechanics shed light on the behavior of particles at the atomic and subatomic levels, painting and giving us a clear picture of the microscopic realm? What makes these postulates the foundation upon which the entire framework of quantum mechanics rests? Can the postulates of quantum mechanics reveal the secrets behind the strange behavior of the subatomic realm? In this video, I am going to answer all these questions, and I will show you how understanding the postulates of quantum mechanics make you understand the concepts of quantum mechanics much better. I am going to use simple and clear explanations, and I will use those mathematical equations which are absolutely necessary and explaining each and every component of the mathematics. We undermined what are the postulates of quantum mechanics, but this video is going to open your eyes and will let you know why and how postulates are very important before we start learning quantum mechanics. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this video on understanding the postulates of quantum mechanics. Before I go ahead in this video, going ahead with the further details, I have a small and an important announcement for you. On the 30th of this month, July, which is a Sunday at 8 p.m. Indian Standard Time, I'm conducting a free live webinar on general relativity, explaining Einstein's field equation, space-time curvature, and an entire journey into general theory of relativity. It will be conducted through Google Meet. So all you need to do is that here is my email ID where you can write me expressing your interest and send me your WhatsApp number so that I can send you the Google Meet link 15 to 20 minutes prior to starting the program. Even if you're not into science, you are welcome to attend this webinar. The basic idea is to clarify the doubts and have a one-to-one discussion session and learn more about the intrinsic understanding and the complexities, making life easy for students who are willing to learn physics and general relativity. So Sunday 30th of July, 8 p.m. Indian Standard Time. If you're willing to participate, please let me know in the email. So first, let us go ahead and understand the topics. Simple, we need to understand why do we need postulates. Are these just mere assumptions or there is a deep and intrinsic philosophy in it? What are the postulates of quantum mechanics? We are going to see a very important, that is the difference between Hermitian and Hamiltonians, and then we will cover first, second, third, fourth, fifth and sixth postulate, and then we will summarize and understand. This is going to be a very important video in your basic and fundamental understanding of quantum mechanics. First, we need to understand why do we need postulates. Are these mere assumption? For example, let x equals to 2, or for example, a variable equals to something, or there is something meaning coming up into this part of our video. So you see, this is a very basic definition of what is a postulate. Scientists have derived a series of axioms and the result are called postulates. That means we have assumed something. Now these are in fact assumptions that we need to make understand how the measured reality relates with the mathematics of quantum mechanics. That means whatever we are measuring in reality, how we can interpret in quantum mechanics. So here is a figurative kind of illustration. The postulates lie right at the base of any scientific theory, and a scientific theory is built on those postulates. These postulates are basically fundamental assumptions and certain principles. But in case of quantum mechanics, you will see these fundamental principles and assumptions are something very weird, something, well, I won't say. Let us look into the next part of our video. So you see, these postulates actually are at the base of the pyramid, that is a building block of any knowledge. It outlines the behavior and the basic concept that rules and quantum systems exhibit. So from postulates we go to the scientific theory, which allows us to describe and understand the behavior of particles at the quantum level. So these fundamental assumptions and principles helps us to understand quantum mechanics better, and based on this, because of scientific knowledge is built, if you do not have the postulates, the entire pyramid of the scientific theory will break down. Now we can develop obviously a consistent and predictive theory of the microscopic world, because we are all doing experiments and we need to predict what the particle or the subatomic particle will be in the next moment of time. That is what the postulates helps us to do. Okay, before we go ahead, we'll take a little bit deeper understanding in this part of the video for postulates. The quantum mechanics postulates are very counterintuitive. What do I mean by counterintuitive is this: they are beyond our intuition, they are very unreasonable, illogical, implausible and absurd. For example, quantum entanglement, for example, superposition principle, and there are a lot many like quantum tunneling, etc. So these are counterintuitive. That means because of their counterintuitiveness, we have taken them as a postulate. You see, in classical physics, what happens is that all those frames of reference, all those experiments which we are taking place are actually very deterministic rather than of the quantum physics. So classical physics, which describe macroscopic objects, cannot fully examine the behavior of subatomic particles. And that is the reason from classical physics, once we are moving into quantum physics, we need to make certain postulates so that we can understand. And classical physics, because it is unable to explain the absurdity of quantum physics, we need to have the postulates. Now the question is that what is the purpose of this postulate? Why do we need at all this postulate? Can we go ahead with quantum mechanics without these postulates? Coming up in the next part of our video. So as we have seen this figure, so the first thing is that they define the basic concepts and quantities in the theory, such as wave functions, observables and measurements. We will see that. So that means the basic concepts are being defined and the postulates are later generalized or put into mathematical equations. The second thing is that they provide rules for calculating probabilities. That means until and unless we have a set of rules, how do we calculate the probabilities wave function for making predictions? So second postulates do provide that. Third is that they establish principles of superposition, wave particle duality, quantum entanglement, other phenomena. That means this is basically considered to be a principle, because we do not have, we have not been able to mathematically or theoretically explain why superposition happens, why there is a wave particle duality, and why there is entanglement. So these postulates are defined right at the base. Based on that, we can do the mathematical calculations of the scientific theories. Lastly, they guide the mathematical formalism of quantum mechanics, because until we put them in a mathematical rigor, until we have a formal definition or a formal way of writing such as Schrodinger's equation, the postulates or the scientific theory won't be dealt with. So these are quite a few of the reasons, as you can now understand, that because of the weird behavior, because of the paradigm shift from classical to quantum mechanics, we need these postulates, and it also helps us in order to do a better establishment to predict the behavior of electrons and subatomic particles and thereby predicting them. So here is a final kind of a, I would say, summary. They represent a mathematical framework rather than a complete physical picture of the quantum world. The question is that why we are telling that it is a mathematical framework rather than a complete physical picture, coming up into the next part of our video. So we will now understand what are the postulates of quantum mechanics, and then you will see we will be able to understand this question, that why they are mathematical but not physical. So there are many definitions of postulates. I have taken in a very simple plain English language the overall idea of these postulates. One is called the wave function postulate, which defines the basic idea of quantum mechanics. The second is called experimental observables, and third is individual experiment measurement. So these 2 and 3 are intimately related to each other. Whatever the experiment and the observables happen, you will see there is a relation with the individual measurement. Then we find something which is called an expectation value and a wave function collapse. Then we find time evolution, and finally something which is known to you, which is called the Pauli exclusion principle. Very fundamental to quantum mechanics. We will take all these postulates from now on in a very simple language, barring the intricate and complex mathematical details. First, let us understand the first postulate. What is that wave function? So what it tells in a very simple language, it states that the quantum mechanical system is completely specified by a wave function. And this wave function, remember, it is a mathematical function, and which just gives us the probability of finding the particle at a given point in space. Nothing else that. So point number one coming up, if this is a kind of a probability density curve which has got a bell curve, then you see these are the electrons, so it might be here, might be here, might be here. So that gives only the probability of the location of the subatomic particle. So here comes the first point. Remember, it is just a mathematical function, not anything physical. And now you see, I was just talking before we summarize the meaning of the postulate that it is more of mathematical rather than physical. So this is the reason that because we cannot see them physically, we try to draw something on a mathematical function. Also, what is important is the probability of finding. That means nothing is definite. So what we deduce from here, the first postulate, how electrons can be found in different places, and it only describes a probability cloud. We will soon see what is a probability cloud, which shows where the electron might be likely to be found. So this is the first basic foundation of quantum mechanics, that wave function contains every single details of a quantum system, but it is a mathematical function, nothing else, and it just gives the probability of finding the behavior or the location of the electron. The second postulate is something which is very central. Now what it said is called the observables postulate. Don't worry with this hat sign of A, I will soon explain to you. Now what it explains is that states that to every observable in classical mechanics, anything which is observable that we see, there corresponds a linear Hermitian operator in quantum mechanics. And observable is a physical quantity that can measure, such as position, momentum, energy. Okay, I will explain to you what is Hermitian definitely. Now if I say that the electron, if I take an electron out of this orbit, right, and I say that the energy of an electron is actually associated with a quantum mechanical operator which is called the Hamiltonian. Now here there are two unknown concepts right now. One is called the Hamiltonian, another is called the Hermitian. Now Hamiltonian is just the addition of the total energy of a system. So you see, it is the potential and the kinetic energy. So Hamiltonian is a mathematical function that describes the total energy of a system. Now why I am defining you Hamiltonian, I will soon come to you will soon come to know, but here you see the energy of the electron is basically a quantum mechanical operator which is called Hamiltonian. Now the wave function that defines everything which we have just defined in postulate 1 collapses to a state. That means as soon as you observe, it collapses to a state that corresponds to the eigenvalues of the Hamiltonian that was measured. So what is going on actually? What is the relation between Hamiltonian or Hermitian? I will soon tell. But remember that energy of an electron is something which is defined by the Hamiltonian, which is basically the addition of the total system, energy system, and the wave function when it collapses as soon as we observe it, it actually corresponds to the eigenvalues of the Hamiltonian. That is the total value. But yet we have said here that it corresponds to a linear Hermitian operator. Let us see what is the link and the relationship between these two things, Hermitian and Hamiltonian. Very interesting. It is actually denoted by this dagger sign, which is Hermitian, and this was found by the French mathematician Charles Hermite. And now Hermitian is basically a general mathematical property which applies to a huge class of operators. What property? Let's hold on for the time being. Let us understand that is a mathematical property and it applies anywhere. Also, this one is basically the sign of the Hamiltonian. This is denoted by hat, and this was basically coined by William Rowan Hamilton, an Irish mathematician. I think he is the first person to quote the term tensor. Now Hamiltonian is basically a specific operator, although it is also general, but in terms of quantum mechanics it encodes the dynamical, especially the time evolution of a system. So what it is here, now if Hermitian operators are the superset which is applicable to all, then we can obviously say that not all Hermitian operators are Hamiltonian operators. However, all Hamiltonian operators are Hermitian operators. I hope this part is clear. Obviously, Hermitian operators are not Hamiltonian operators because Hermitian is a very general class of operators. But all Hamiltonian operators, which are this subclass, falls under the category of Hermitian operator. So all Hamiltonian operators have to be an Hermitian operator. So we deal with two operators right now. One is the Hermitian, one is the Hamiltonian. Hermitian is the superclass which consists of a huge class, but it cannot be Hamiltonian because Hamiltonian is subclass. Hamiltonian falls within the Hermitian, so obviously all Hamiltonian operators are Hermitian. Now this is something very central to quantum mechanics, and we will soon see that how important it is. So what is an Hermitian operator? So we say that a Hermitian operator is some kind of an operator which has the property of being equal to its own conjugate. That means, for example, if I take the operator and then we take a complex conjugate of the same operator and then transpose it, that means we swap the columns, we get back the original operator. You see this example, this is an Hamiltonian, and if you take the complex conjugate, it gets back to it. So the conjugate transpose of the position operator, for example x, is the same as the original operator. So the position operator now becomes a Hermitian operator. Why? Because once we transpose or we do the conjugate transpose, we get back the same operator. This is very central in terms of calculating further energy and other things in quantum mechanics. So we understood that Hermitian operator is something that when you conjugate and transpose it, it gets back to the same. So the Hamiltonian operator we just learned has to be an Hermitian operator. Why? Because the eigenvalues of a Hermitian operator are real numbers. When we are dealing with energy levels or when we are quantizing something, that means what? We need something physical. And in order to become something physical, the eigenvalues of Hermitian operators are real numbers. And that is the reason why this is so. The energy of a particle have to be physical. It cannot be anything superficial. So if the energy of a particle is physical, then it has to be measured. And what does measurement means? It means physical quantities. And what does physical quantity means? That the Hamiltonian operator, which is the I would say the general class, has to be Hermitian. Let us see a few more examples. This one become clear. So the Hamiltonian operator has to become an Hermitian operator because in order to specify or calculate the energy of a particle, we need something physical. So here is a quick example. Let us check x squared is Hermitian or not. So we just take this simple mathematical calculation. The next step follows, and from here you see we get x squared. From that we can deduce further a equals to x squared, and the Hermitian is x squared. So we prove that x squared is Hermitian. You can skip this part. I mean to say you don't need to be that mathematical, but this is a very simple deduction. I just thought to show you. So here are certain important points. The eigenvalues of Hamiltonian operator has to be always real because we are energy measuring physical system. The operators of all physically measured quantities are Hermitian, and therefore their eigenvalues are always real. The operator itself, for example, if I'm drawing in a matrix, it can have complex matrix element, but the eigenvalues has to be real. And while an Hamiltonian must be an Hermitian, it might happen when we're plotting in a matrix. It can be either real or complex, but the eigenvalues has to be real. So what we can tell from here, that Hermitian operators are a general class of operators that have the property of being, that adjoint. Hamiltonian operator is used to denote the total energy of a system, which is called how we use the time evolution of the system. So Hamiltonian is a specific operator in terms of quantum mechanics, right? And it encodes the dynamics, especially for the time evolution. And the operators of all physically measurable quantities has to be Hermitian, and therefore they have real eigenvalues, and the eigenvalues of the Hamiltonian are always real. From here now you see the second postulate, it will become clear. The second postulate states that every observable in classical mechanics, there corresponds a linear Hermitian operator. Why Hermitian operator? So that it is something which is real. In quantum mechanics, an observable is a physical quantity that can be measured, such as position, momentum, or energy. If you really want to go back, you can go back to this particular part. This one, you see the position operator is a Hermitian operator because once we conjugate it, we get back to the original operator. Because the eigenvalues of the Hermitian operator has to be real numbers, it is physical quantities. If you further want to go back, you can go back here. that Hermitian is a general mathematical operator and Hamiltonian is something specific. So from here we deduce this, and from here we get to into this. This is a check and these are the relevant points, and here we see this is the one. So right, so the Hamiltonian operator is the total, Hermitian operators is a general class, and the operators are of physically measurable quantities are Hermitian, that has to be physical, and the eigenvalues of Hamiltonian operators are always real. So here comes the final, this is just a kind of a revision, that there corresponds to linear Hermitian operator, and that has to be real. Now we come to the third postulate. Now you see what you have learned from we have learned from the Hermitian operator, etc. Some part of it will be common. What is the postulate? It states that an observable, now you understand what is observable, is measured, the wave function of the system collapses to a state that corresponds to the eigenvalue of the observable that is measured. Now when it collapses, what happens? It has to be real. So it has to be a Hermitian. Okay, so this is a kind of a schematic diagram. You see that the wave function is, when it collapses, it takes a very narrow sharp turn, where before that it was quite wavy kind of a thing. Now it explains why we only see certain results when we measure quantum mechanical system, even though the wave function of the electron describes a probability cloud. That means the certainty or discreteness of the quanta which is measured is being dictated by the third postulate. Now what do I mean by probability cloud? You see, from the Bohr's atomic model we have now moved to this new model. So you see the nucleus and the electron cloud. This part actually shows the cloud of probabilities. That means what it shows, that the more the dense the cloud it is likely that the electron has to be there. That is why it is called cloud of probabilities. Where the cloud is most dense, the probability is more, and where the electron is less likely, the cloud is less dense. This is what is called the probability. But what is important is that only we see certain results because the wave function collapses, and it collapses with the corresponding eigenvalue. Okay, this is actually what I'm trying to say, that this is the central point of quantum mechanics. Way back from the first Solvay conference, when we started learning quantum mechanics, we learned that nature is discrete, nature is quantifiable. This is the thing which is coming up. So the values of dynamical variables can be quantized, although it might have that the eigenvalues might have continuum in case of an unbounded states. So if I take this kind of a thing, that A, which when operated it gets an eigenvalue, this has got an eigenstate to eigenvalue. So any measurement of the quantity of this operator A will result into this A. And what I am trying to tell is that measurement must yield an eigenvalue. The state might not have to be in an eigenstate of A. So the measurement has to be A, and that shows that how we can quantize things. So if I take an arbitrary kind of a thing like this and I can expand into this kind of equation, what it tells that n definitely can go up to I to infinity, but measurement of A will always result into AI. But which one prior to the measurement we don't know. So you see the very central part, the philosophy of quantum mechanics, is revealed in postulate number 3. And it shows that nature is quantifiable, and why we get only a definite value, this is the reason. It collapses to eigenvalue, which gives a real value. Coming up, postulate number 4, even more interesting. This is something which is called the expectation value and collapse of the wave function. What do I mean by that? This is a little bit mathematical, but I will make it simple. If I take a system, obviously we will define it by psi, that is a wave function. Then we take an average value of the observable, and this average value is given by this kind of a mathematical equation. I will explain you the components one by one. See, this is basically the expectation value of a physical quantity, for example A. This entire integration from plus infinity to minus infinity is basically the average, but the average is for a wide number of large numbers. This one, which is got a hat on this is the operator that represents the physical quantity A. This one obviously is the wave function, and this is something which is called a volume element. Now I can talk a lot about volume element, but let us understand it is the tiny, very infinitesimal small differential element that we are considering. In quantum mechanics, we are considering this. In classical mechanics, it can go up to spherical structures, it can go into polar coordinates, but it is basically a volume, a place which is very, 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 very small. We are differentiating it. So we get the expectation value, we are averaging it using the plus minus infinity, the integration sign, and we have got the operator, we have got the wave function, over it we have got the volume element. So what it tells is that in general, if I don't take this one, this is very specific, but in general what we can say is this, that any observable quantity, for example this one is A, so if I take any observable quantity, we can put this into the quantum mechanical operator in between the observable and the wave function. For example this one, I take something like this, and this is the Q, that means any operator, and you see it sits between where? It sits between the integral, that is average, and this one, the integral over space. That means the I would say the infinitesimal, the volume element. So that means any kind of an observation, any observable quantity, using this format we can put it. Coming up, postulate number 5. This is called time evolution. So you already got the int. It is nothing but this one, the Schrodinger's equation. The wave function actually evolves as time passes, and it is being dictated by this. Okay, I will just let me explain you one by one little bit about these components. This h hat is basically the Hamiltonian operator. This is the wave function. This r is basically a radial coordinate. Basically it is a vector, so it is written in capital. T is obviously the time, I is the imaginary number, h bar is the Planck's constant, and this gives the partial derivative with respect to time. That means still how the wave function changes as time passes. Because we are, if a system is evolving, then we need to find how the system is evolving along with the passage of time. So this is how it looks. Schrodinger's equation has got a huge implication. I can make maybe 2, 3, 4 videos separately, but this is what the time evolution talks. So what does the Schrodinger's equation tell us? It describes that how the particles or the electrons will change over the time. It also tells us that how can we find out the behavior of the particles in quantum world, and the Schrodinger equation helps us to understand the behavior of the tiny particles, and it describes the probability of the positions, making quantum mechanics an essential framework to understand the microscopic world. Okay, so finally we come to the 6th postulate. Not much to explain, you all know, that is called the Pauli exclusion principle, that no two identical particles can occupy the same state. What do I mean by that? That means if I got a spin half particle which is a fermion, it has to be, I'm so sorry for the spelling mistake, it should be anti-symmetric with respect to the interchange of all particles. If it has got a spins positive, that is 1, these are called bosons, and it has got a wave function which is symmetric. This is which is a mathematical derivation, which is a definition which is called the fermions. I've taken a spin half, and this is what is called the bosons. Pauli exclusion principles have a lot of implications in cosmology and other things. I'm not explaining it further. So that's it for all the 6 postulates. Let us summarize quickly. This was the wave function which actually defines the quantum mechanical system, and it depends on the coordinates of the particle. Second was the experimental observable, and we have seen that it corresponds linear Hermitian operator in quantum mechanics, and it is an individual measurement. It is basically how the wave function of the system collapse, and that eigenvalue gets one value in terms of observation. Expectation value and wave function, I'm not explaining it, it's quite mathematical. The explanation explains it. Time evolution is guided by Schrodinger's equation, and the Pauli exclusion principle ensures that no two electrons with an atom can have identical quantum states. What do we mean by quantum states? The boson and fermions I have already informed. So that's all for today's video. I hope that I have been able to establish the fact why postulates are extremely important in quantum mechanics, and I'm also thankful for taking up time to watch this video. Please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notifications, students, and if you have liked the video, please click on like. This is my email ID as usual, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. I have a separate channel for general relativity. You can subscribe to this, and this is where I keep on posting something new about science, discoveries, biographies, and a lot of informative stuff. You can follow this as a page in in Facebook, that is Hawking Life and Works. Thank you very much for watching this video. We'll be back very soon with more interesting videos. Stay tuned with Physics for Students and learn physics and be happy.